This is the SOLIDNotes webinar series by DesignPoint Solutions. My name is Sam Saloom. I'm an application engineer here with DesignPoint Solutions. This is the 15th installment of the webinar series. In this webinar, we're going to discuss large assembly designs and how to optimize your performance using large assemblies. From here, I wanted to make a note that a lot of the information that I'm getting from here is either through the advanced assembly class, which DesignPoint offers. If anybody's interested in that, please let me or, and I'll show you my email at the end, either I or one of your account managers know. Along with that, I also got a lot of my information from a step-by-step guide for improving large assembly design using SOLIDWORKS, and this is written by SOLIDWORKS themselves. So I would imagine they know exactly what they're talking about since they designed the software themselves, and it gives great tips and tricks on how to optimize your design, and I'll probably be, a lot of the information I'm pulling is going to be coming from there. So let's go ahead into the next slide. And let's talk about what a large assembly is. So usually what I get within the classes is how many components does it make to make up a large assembly? How much is that? Is it like 200, 300? How many components makes up a large assembly? And I always answer it the same way. I really don't know. And the reason why I don't know how many components make up a large assembly is because I don't know how you particularly would model that assembly. So with a large assembly design, it's very specific towards you as the user. As far as, in SOLIDWORKS, you can control about 80% of the stuff that's going on around within SOLIDWORKS as far as its performance. And then the other 20%, is kind of out of your hand. It's probably due to hardware or software issues. But anyway, so that's the answer is what really makes up a large assembly. The real definition for it is basically an assembly that is that's just using up so much of your system resources that it's making the model noticeably slow. So that's what a large assembly is. It's using all or a large amount of your resources to cause your machine to slow down. So what can cause that? Well, your SOLIDWORKS could be, or your assembly within SOLIDWORKS could be doing too much stuff, and that's too much stuff for your hardware to handle. So that can mean you have too many components, you have too many mates, your features are too complex, or you have too many external references. As well as, your hardware is just not up to speed with SOLIDWORKS. It's probably not using the recommended settings for SOLIDWORKS. So the too many components thing, we can't really control that. I mean, I don't think you guys have really that much control as far as how many components you would like to use. But you can control how many mates you apply, and we'll probably discuss applying mates as well as how complex your features can be and any external references that you may have. Those are things that you can all control. So for the most part, your hardware and then the actual software, you can't really control that. But for the most part, you can optimize your design for performance reasons. So let's go ahead into the next slide, and we'll discuss. There's kind of 4 different ways of kind of broken up this webinar into 4 different sections. In each one of these sections, we kind of discuss how to adjust your settings to be optimized for performance, how to efficiently model your part, as well as how to efficiently model the assembly, and once you've adjusted your settings, you've modeled the part correctly, and as simplified as possible, you've modeled the assembly as correctly as you possibly could, and you follow all the right steps there. Once that happens and you're still seeing a reduced performance, what you can do is you can kind of reduce some of the information loaded into memory using some of the tips that we'll describe in this webinar. First thing I want to do is make sure that everybody checks their hardware and make sure that it's up to speed with SOLIDWORKS. SOLIDWORKS on their website has a system requirements page. Please make sure that your machines are up to performance on the system requirements. As far as the hardware, one of our application engineers created a blog on how to make a workstation or how to buy a workstation that's cost-effective and optimal for SOLIDWORKS. So they'll talk about the different components within SOLIDWORKS in this blog, and also discuss some of the best recommended paths towards which component to buy and then how to use it with SOLIDWORKS. So that's in this blog here. All you have to do is just go to our design point page and go to our blogs and then look up hardware requirements for SOLIDWORKS and you'll find it there. Along with that, and if you've ever called me in technical, if you've ever called I or any one of the application engineers within technical support, we've probably told you that, and we've probably done this where we've checked your graphics card and we had to make sure you're using the right graphics card driver. It's very important. For the most part, what you're doing is you're viewing a model and you're looking at it, so a graphics card is going to come in a real big handy in that situation. So you want to make sure that you have the one that's certified and tested by SOLIDWORKS, so that you know, it's not any graphic issue, not seeing any weird graphic issues from that. So please make sure that you guys are using the right hardware to use SOLIDWORKS. That's a good stepping stone. That's a good start. And then from there, there's the SOLIDWORKS system options. So there's some options that you can change to edit your performance. Let's go ahead and open up SOLIDWORKS. We have SOLIDWORKS open up over here. And let me go ahead and open up, actually, let me open up this part. So if I go to options, and then I'll go under the performance tab, you'll see where the verification on rebuild is. That's that first option. So what this does is it, and I'm just going to go through some of these options. I don't really have time to go through all of these options as far as what's under the general drawings and whatnot, because but all these options are covered in that step-by-step guide that I mentioned before as a reference. So that guide can be very helpful in understanding what these options do. Okay, so the verification on rebuild, what that allows you to do is it checks a particular face or one face, and it checks it with all the other faces within the within your assembly or part or whatever it may be. So it verifies that, you know, the model, the geometry is correct. There's not any strange or inappropriate geometry going on. By having this checked, usually what it does is if with this cleared, it'll still check, but it'll check all surrounding faces. This is an option, a good option to try every now and then to turn on and then do a rebuild, but this isn't something that I would recommend constantly having turned on, just because it's probably going to take a lot of time, or it's going to take an extended amount of time to build a model from there, especially if you have a large assembly. Transparencies. So these are controlled, and let me close out of this part. Let's go and open up a large assembly, or just a regular assembly, just to show you what transparencies do. And I just have a regular assembly here. And if I go under the performance tab and I turn off the high quality, well, actually, yeah, let me turn off high quality here for transparency, and let me keep that turned off, and I click OK. And now I'm just going to go ahead and click on this part and make that transparent. So what that actually does is that reduces the quality of transparency. Now if I go back and I turn that option back on, you'll see here it increases the quality of that particular transparent part. So it's always a good step, and it's always recommended that for performance reasons you just have this turned off. Along with that, next is the level of detail. So that describes how much level of detail is going on within either your part or assembly. Typically, it's a good idea to keep that on less level of detail. That way it's moving faster, and you can actually rotate the model and adjust it faster. If you're seeing issues with rotating your model, check this setting and make sure that it's on less or it's turned, well, actually I would make sure that it's on less. Along with that, under the assemblies, you have the option to automatically load components lightweight. So what a lightweight component is it's a component that kind of has some of its model data reduced. So what that basically means is it doesn't load everything within the model, it only loads what it necessarily needs. So you can still select faces, edges, and you can still make components. And there's a lot you can do. The only thing that you can't do with a lightweight component in an assembly is you cannot edit the component, and you won't be able to see that component in the feature manager design tree. But for the most part, this is a very good thing to keep checked on. And especially if you're dealing with large assemblies a lot, you want to light your components at all times. And you probably want to keep the always resolved sub-assemblies cleared because you want to use that as much as possible. For checking out-of-date lightweight components, You do want to know when your component or lightweight components are out of date or need to be rebuilt. So that's why it's always a good idea to check that option to indicate. Resolving lightweight components. If your assembly needs to be resolved, if the components within your assembly needs to be resolved, what it can do is you can click on here and then go to always, and it will resolve those for you. But for the most part, I would just leave it on prompt. That way it asks you. That way you know when you go to make an edit that you're going to go from lightweight to resolved instead of just automatically doing it. And then the rebuild assembly on load, you can specify to turn that off or to keep that on always. What I would probably do is leave that on always. That way you know when you're loading. So what it's going to do is it's going to rebuild the assembly. That way you know that you have the most up-to-date part. So I would just leave that turned on, even though it's going to take a little bit more time to open up your assembly because it has to rebuild it. Mate animation, you could probably just turn that off or switch that to fast. So how you mate two components, if you select one component and then the other component, you'll notice a little animation where one component's they're kind of combining together, say if you had a coincident mate. So for this step, I would just probably turn this off or just make it fast so that way, if you make it slow, it'll have to calculate a lot more intermediate steps. And then the last thing I want to discuss with this tab is the Use Software Open GL. So what that does is this checkbox here, and it's cleared out now because I have a part open. Let me actually close out of that part. And that's what it actually does is instead of using your hardware's graphics or your graphics card for displaying the graphics, what it actually does instead is it uses the software's display the graphics. The software's information to display the graphics. So it uses the software's OpenGL instead of your hardware GL, OpenGL. So this is a good option to leave cleared. If you don't have any part open in the background and you're seeing this checked and then you're not able to uncheck it, that means you probably have some kind of issue with your graphics card or your graphics card driver, so you need to look into that because what that's going to do is that's going to take a lot more CPU on grab a lot more CPU or processing power from your actual machine, and it's going to slow down your machine a little bit. And also, the little preview that you might get when you're opening a file, it's actually recommended it will be faster if you turn that off. Now under Assemblies, you'll see large assembly mode. And what large assembly mode is, it actually just adjusts some of your settings for you in order to turn them off. So when you use large assembly mode, what that actually does is it changes a bunch of these options here. And it'll either turn off the drawing options or it'll turn off some options here as far as showing contents while dragging the drawing view, or it'll change transparency, it'll turn off the high qualities. And then it'll adjust the level of detail to minimum. So it'll adjust all these system options for you so that, and it'll make sure that real view graphics is turned off. It'll adjust those options for you so as to optimize your settings as best they can be. So I usually would recommend just using that instead of actually messing around with your settings yourself, just because you can always turn that on and off, and then when you're not working with a large assembly, you might not necessarily want some of those options turned on. All right, and you can specify when large assembly mode when an assembly should automatically open up within large assembly mode. For here, we're specifying that after 100 components, it should automatically open up using large assembly mode. By default, I think it's on your machines it will be like 500. And then once large assembly mode is active, you also have some other options. You can not save your auto recovery information. You can hide all planes, axes, and sketch curves, and all shaded with edges will actually just be shaded that way the software doesn't have to calculate the edges. So those are a few of the system options within SOLIDWORKS. Another thing I wanted to point out is, and if I just go ahead and open up, appeared on my other screen, sorry about that. Go ahead and open up the just a part, and if I go to document properties and then image quality, I can adjust the image quality. So you'll see here if I move this from shaded and draft quality all the way down, my circle ends up looking like a hexagon. And if I move it all the way up to higher, where I'm in the red zone, this is going to increase the file size, and it's going to reduce my graphics performance and increase memory usage. So you probably want to get this as relatively low as you possibly can until you don't really notice it being an issue. I'll just hit OK there, or actually I'll leave it where it was before. All right, so that's some of the settings within SOLIDWORks. One thing I want to discuss next, and using large assembly mode is a good way to turn some of those settings, all the easy ones, on and off. So now let's discuss how to efficiently model our part. So one thing I want to discuss is the origin location. So you want to kind of remember how we said in the beginning, what things we want to reduce are mates, external references and whatnot. So the best way to kind of reduce or remove mates is to actually, when you model a part, if you create the origin of the part at the same point where the origin of the assembly would be, you can then fix that part into that assembly. And I actually have that done in a test assembly I have over here. So you'll see this assembly here actually, and I'm going to say right now that I probably don't recommend you guys go ahead and do this, but this is just an idea of how it would look like if SOLIDWORks were set up without any mates, which is probably the most optimal method there can be. From this assembly, you'll see that I have 5 fixed components. And how they were inserted was, well, first of all, you'll notice when I go and open up one of these parts, the actual component is here. But if you take a look, its actual origin is somewhere over here. So how I insert or how I alter this part is if I go ahead and delete this guy here. So I go to insert components, and then I go ahead and insert this component. Instead of just clicking it somewhere way out here and just inserting it anywhere, I'm just going to go ahead and hit the green check up here, and that'll automatically take the part origin and assign it to the assembly origin. So from there, that's how that component is, applied at the origin. So this is probably the most optimal one for performance, but again, I probably would not recommend you guys actually modeling your parts this way, just because if I go ahead and I change a dimension there, it's not going to propagate and it's not going to update because they're not really referencing from one another. So as this might be the most optimal, this is probably not the most recommended way of modeling your origins. What I would probably recommend doing instead is just modeling using or creating your part with reference to its standard plane. So the standard planes, the front, top, and right plane, all go through the origin. And as long as you set those locations at basically mating surfaces, so instead of selecting a face to mate, you would select those planes as what you would use for mating. What that'll do is, it'll be able to calculate those more efficiently. And since those mates, or since those planes are always there within your part and you can't really change them, you can only change the part itself, you won't really have any issues with mate errors along down the road once you make a change or anything like that. So it's always recommended to use your standard front, top, and right planes for mating within an assembly. So that's why it's a good idea that you locate them at a correct location for your origin. Now, in discussion with in-context modeling, so in-context features in a part actually reduce performance as well as in an assembly. And just the reason being is because now that part needs to reference another assembly in order to work. So once you're dealing with large assemblies, I would avoid using, if you need to use one, if you really want to capture a design intent, that's fine. But I would really just recommend avoiding using in-context features as much as you can, because they can reduce performance because it has to load the assembly model, it needs the assembly model loaded in the part, and then as well as it also needs, if there's any faces that were mated using that in-context part, it's going to have to solve for the mates again, and you might have to do them twice. And I'll discuss that a bit later once we talk about efficiently assembly modeling. I would also recommend creating simplified configurations. So what I would do is I would create a separate configuration from the one you have, and you could use that configuration to only mate the faces, or to only create faces that you need mated, or faces that you need to check with interference. So any other faces, such as like a fillet or a chamfer, I don't really recommend that you would just go ahead and use those in the assembly. What I would recommend doing is just creating another configuration. So something like this. Let's go ahead and open up this other component. Something like this, I would probably recommend, suppressing the features, such as these fillets. I'm going to go ahead and suppress some of these fillets. And actually, I should have done this in the, let me unsuppress them. What you would do is you would go under the configuration manager, add a configuration, and then you would go ahead and let's call this configuration simple. So this is a simplified configuration, or simply. Wow. Okay. And then you'd go to the fillets and you would suppress those. So this is our simplified configuration. So we would actually insert this configuration into our assembly model instead of the one with more features in it. So the less features you have, the less it has to calculate for loading the model. And let's say, I don't need these ratchet holes or the wheel hole. I don't need the holes there for any particular mating or to check any interference. Well, what I would probably do is I would probably just suppress them if they're just there for, because you kind of need them to create the part, but you don't really need them to mate them in the assembly or the to check for interference. And then I would go and take that component and insert this configuration into the assembly, while this configuration does not change. And you can create a drawing of this one. All right, so I guess the idea here is to keep it as simple as you possibly can whenever you're dealing with large assemblies. And let's go back. So that's the idea with your part modeling. You want to keep them as simple as you possibly can, just because that's the way to increase performance. The basic idea within increasing performance, as far as a graphic standpoint, is if it looks good, it's probably going to decrease performance. So if it's visually, desirable, it's probably physically going to reduce performance in some way. So for efficient assembly modeling, so how, when you go and you open up an assembly, SOLIDWORKS runs through some steps. So what it does in order to, and it goes ahead and builds the model. When it builds the model, what it does is it loads the components, then it solves for the mates, then it solves for any assembly features, and it solves for any in-context features. So with that said, let's go ahead and open up the model that I have here. So this model has an assortment of all, assembly, in-context, and whatnot. Starting from the top down, first thing it does is it loads the the components. So it creates all the components or loads them from their files and then inserts them into this assembly. And then after that, it solves for all these mates and it does it simultaneously. And I'll talk a little bit in a second about how the mates are actually solved. But first, next, it solves for all the mates, and then it creates the assembly features as well as the in-context references after that. Now, the in-context references in the assembly are shown as update holders. So if I right-click on the top name there, and then I click Show Update Holders, you'll see the in-context references being displayed here, and this is how they update them in the assembly. So if I mate a particular component, let's say I mate, a part with an assembly feature on it, or one that's being referenced by an in-context reference, it'll then have to go down, since I've changed that part, and have to go into here and resolve for the mates to make sure that there's no conflict going on within the mates. So that's why it's kind of unrecommended to use. It's kind of recommended to avoid assembly features and in-context references. If you need to use them, go ahead and use them. but that's kind of the first place I would, or one of the first places I would look as far as whenever you get into trouble with your assembly modeling. So again, it's probably, like I said, if you need to use them, if you want to capture design intent, if it's really important, that's probably why I would use them. But the way I'm looking at it here is just strictly on a performance basis. They kind of hurt you in that department. So now let's talk about solving for mates. So how SOLIDWORKS actually solves for mates. And this, I like showing these images because they kind of strike fear in every young engineering student's heart. Because what this basically is how SOLIDWORKS solves for the mates is they use a system of equations. And what that does is, when the more equations you have, the more complicated the system of equations can be. That means that the more time it's going to take to solve for it. The more equations you have also includes the more potential issues that you might have for you getting mate errors. And then the more problem it might be for troubleshooting that. So you want to keep the mates as low as possible, and you want to reduce the amount of mates that you're using. And also you want to keep in mind on ways to optimize mates, and here we'll discuss that just as well. We'll discuss that. So based on that information, a good mating scheme would be one where you're taking one component as the base, and then all other components are mated to that particular component. This is probably most ideal for performance. A mating scheme to try to avoid is you have that one base component and it's being mated to one component, and then that component's mated to another, and then that component's mated to another, and then that component's mated to another. It's just on how it solves it. It doesn't really like that, and it likes this more. So again, you want to try to use this more than the other two. And then down here, you want to avoid any circular references with your mates. So you want to avoid any circular paths that you're creating, so that's mated to that, that's mated to that, that's mated to that, which is back really mated to the original, just because it's a little bit harder for it to actually create those mates. All right, so what are some good ways to avoid, creating top-level mates? Well, the best way to reduce the number of mates that you have without actually having to reduce the number of mates that you have is to create subassemblies. And what subassemblies allow you to do is they allow you to take your mates, and with a subassembly, it basically, in SOLIDWORKS, it treats the subassemblies as basically like parts, almost. So it kind of ignores the internal mates within that subassembly, and there's not really any motion allowed within the subassembly, unless you make that particular component flexible. A flexible subassembly allows the motion to appear within that subassembly. Where that goes wrong is, here's how it calculates flexible subassemblies in regards to mates. First, it'll calculate the mate in the top-level assembly. Then it'll go ahead and calculate the mate in the second-level subassembly. Then it'll go back in the top-level assembly and make sure that there's no interference going on with the mate in the second-level assembly. So it creates basically an extra step whenever you use flexible subassemblies. And almost, to me, it seems like it's almost better just to not use flexible subassemblies when you want to show it that way. So I kind of recommend avoiding using flexible subassemblies. But using regular subassemblies, rigid subassemblies, is very ideal because that'll reduce the number of top-level mates you have, which will reduce the calculation that's needed to be done in the top level. Also, you want to avoid any redundant mates. So if you're mating one face to another and you're using a coincident mate, you don't really need a parallel mate applied to that same face, just because, when you make it coincident, they're technically already going to be parallel anyway. So avoid any redundant mates. And SOLIDWORKS isn't going to get over-defined by those mates either. So, if you don't really need a mate, try to keep it just down as less as possible. It'll still be able to solve them. Doesn't necessarily mean it's over-defining because it's still able to solve for that equation. It's just, it's just more an extra step that's not needed. And avoid mating to time-dependent features. What I mean by time-dependent features is I mean by assembly features and in-context features. Since those are kind of solved in a hierarchy, in a timeline. So this cut extrude is going to get solved, and then that's going to get solved, that's going to get solved, and then it's going to create these features. So these are kind of solved as if they were in a part, like a features-based part model. So you kind of want to avoid mating to these, just because then after that it has to go back and recalculate the mates. Now, what I do recommend doing is I do recommend involving patterns, even though they're kind of, okay, so usually it's a good idea to kind of not mate to anything underneath the mates folder. That's definitely a good idea, and it's also a good idea to avoid using anything that you would have to put under the mates folder, except for linear patterns. I definitely recommend using component patterns, because that way you don't have to create as many mates if you're using the patterns. So it's definitely a highly recommended feature to use. Along with that, so the last thing I want to discuss with respect to this is mate performance. So found in that step-by-step guide, it actually shows which mates actually perform quicker as opposed to which mates actually take more time to perform. So you'll notice here that the fastest mate under the mate performance are relation mates. So these are your basic coincident parallel mates. Well, your logical mates, like your width and your cam, your mechanical mates, those guys don't perform as fast. And then the slowest ones that are going to take the most time are your distance, your angle, and your limit mates. So those guys just take a while to calculate, just because they haven't, that added dimensional value to them. So the ones that are produced the fastest are like coincident, parallel, tangent, concentric. Those are basically a mate that can be defined in a relation. That's going to get you the best as far as performance. That's just something to keep in mind. I'd probably avoid it. I wouldn't necessarily not use these. I mean, there's definitely going to be times where you're going to want to use a distance mate, but if you can do it without it, try it. Okay, so along with that, the fourth thing we're going to discuss is how to reduce information loaded into memory. So opening assemblies in large assembly mode and lightweight is going to be very helpful. Using the option to selectively open an assembly can be helpful as well as taking a display state, and from the shown components in the display state, you could choose to unload the hidden components from there. And then you could use speed pack when you've kind of exerted all of that, or when you have a sub-assembly. So let's talk about opening assemblies in lightweight. Let's go ahead and do that. Let me close out of this assembly. So you'll see here in SOLIDWORKS, since I have, passed the threshold, or I think since I actually let me go back and show that. Let me show you how I opened that up again. So let me go to the top level assembly here. If I click on this, you'll see here under mode, I can open it up in large assembly mode. I could also open it up in lightweight, but once you open it up in lightweight, it's going to open it up in large assembly mode. Or once you open up large assembly mode, it'll open up your components in lightweight as well. So I'll go ahead and do that. And from there, what it does is it lightweights the component. So you'll notice if I try to look at inside of a particular component, I won't see any of its features in the design tree, and I can't go and edit that component. And if I do try to edit the component, it's going to resolve the component. As you can see here, it resolved that component in order for me to edit it. So let's go ahead, and if I just right-click on that component, I could set it to lightweight. Okay, so that's opening up components in lightweight. You'll notice that your assemblies, for most part, should run a lot more smoother once they're in large assembly mode and your components are lightweight. Let me go back and let's talk about the next topic, which is selective opening. So you could selectively choose what components you want to open. Let me go ahead and close out of this. And how I would do that is I would open up the assembly in large design review. So you have to open it up in that mode, and then you hit open. And what large design review allows you to do is it allows you to navigate the design tree selectively open components is what we're going to do. Measure the distance, create cross sections, hide and show components, create display states, and then create walkthroughs if you have a plant layout where you can actually walk through the particular component. Okay, so based on this, I could specify which components I want to open. So if I click on selectively open and I select the components that I want to open, let's go ahead and select that component, this one, that one, as well as that one. And you know what, let's not use that one. And I'll just hit open selected. That'll only actually open up those components I had selected. So what that does is that hides all the other components. That's what this warning box is telling me. And it doesn't load any of the hidden components into memory. So right now, the only thing that's loaded into memory, the only thing that's really open here, are the components that you're seeing on the screen. Now, usually when you hide a component, usually when you hide a component that is already loaded, it's still loaded into memory. It's just not visually seeable. You visually can't see it. But for this particular case, whenever we hide a component, when we open it up using that selective open option, it's hidden. Now you could also use that ability to unload hidden components by going, let's go ahead and switch to this display state. If I go under this, if I right click on the top level assembly here and I hit unload hidden components, I could also use that option to not, load the hidden components. So right now the only thing I have loaded into memory, or the only thing I'm really working with here, is the portions that you're seeing here. Okay. Then I could also, so that's the display states, and then there's also the speed pack option. So if I create a speed pack, and I'm not really, kind of running out of time here, so I'm not really going to go into that much detail about a speed pack, but what speed packs do is they allow you to take an assembly and you basically show you take a subassembly and you basically show the speed pack version of that subassembly. So basically it doesn't really load most of the model into that assembly, and all it really loads, if I create a mated speed pack here, what it does is it creates a configuration where, with the speed pack, where I really can only use components that are mated within that subassembly and the actual main assembly. And you can see here it kind of ghosts out all the other components that haven't been mated to the actual main assembly. I could hit Alt S to remove this ghost here, and if I try to make selections, it's only going to let me use the ones that have been mated in the assembly. So it's not loading most of this subassemblies, most of the components within the subassembly. And then along with the speed pack, there's only one more thing I really wanted to show. Assembly Expert you can look up, as well as feature statistics to understand how the models are created, and you can use those to kind of identify it. But one thing I really wanted to show is an assembly visualization located on the Evaluate tab. You'll see here, if I click this arrow here and then go to More, I can go under Properties and look up the graphics triangles, and then hit OK. So I can actually see which components within my assembly are causing the most graphical issues with me, or causing the most time to load. And you can see those graphical triangles here. So in this case right here that I have, this rock grate, the component next to that has about half as much graphical triangles as that one. So that's why in this situation I would actually look into this component and look for ways where I could reduce, and you can see how complicated this component is, look for ways where I can reduce this particular model in order to better have it use less graphic triangles. What I would probably do here in this situation is change the layer patterns to show a geometry pattern, as well as, instead of, I think this one uses, for this particular part, it uses a features to pattern, features and faces. I'd probably check that and use just select a bodies to pattern instead. Oh, cancel out of that. Go back into this one. Yeah, so this one uses a features and faces pattern. I'd probably just use like a bodies pattern instead. Just because that'll probably reduce the performance of this part a lot more better. Oh, I messed something up here. Okay, but anyway, I'm not so sure what I did to screw around with that. But anyway, we'll go ahead and we'll go back and that'll kind of wrap it up. Like I was saying, I could use that assembly visualization. The big takeaway from that is I could use assembly visualization. I could use assembly visualization to understand the graphic triangles within my model. Okay, so that kind of wraps up this presentation. So if you guys, I want to thank everybody for coming out and listening to me talk about large assemblies. I apologize for going over time. But anyway, if anybody has any comments, questions, or suggestions for future SolidNotes webinars, as well as any comments about this current one, please either leave it under the questions. I'm here to take any questions that need to be answered right now. And you can also email me directly if you have any comments or questions. If you need any immediate assistance, any immediate technical support assistance, just email us at support@design-point.com. So now I'll go ahead and answer some of the questions. So one question I have here. Okay, so we've already started. The second question is, so when you use software GL, you'll manipulate the assembly faster than the hardware graphics card? No, that'd be the exact opposite actually. When I use software GL, OpenGL, that takes time for that. What that does is the software is actually calculating the graphics there, and that's going to take more CPU power from your machine, which in the end is going to hurt you when you're modeling in SolidWorks, because now there's more processing power being used outside of what normally would be because you're using software OpenGL. So you definitely want to leave that cleared. Make sure use software OpenGL is cleared and it's not selected, because you want to use your hardware graphics card. That's going to move a lot faster, just because it's going to take less processing power on your actual machine. For imported parts, another thing that I also might recommend is if you have a file that you probably don't plan on making any changes to, saving it out as a step file and then bring it back into SolidWorks where there's only one feature there and it's just showing an imported body can be very helpful. We didn't really have time to get to it, but also the defeature tool can be pretty useful in that situation as well. Does anybody else have any questions at all for me? No? Okay. All right. Well, so that's going to wrap up this webinar. So if anybody does have any questions, go ahead and reach out to me either by my email or through our technical support. And thank you. That's how we'll end it.